All right, welcome back. So this time we're going to do the second part of this proof of Jacobson and Rickart's. Let me just remind you what we're trying to show. So what this theorem is about is we have two associative algebras and a Jordan homomorphism between them, and we're going to try to show that that would imply that this map is either a homomorphism or an anti-homomorphism. The overall theme being that the Jordan structure carries a lot of information, not everything about the associative structure, but a lot. So if sigma from A to B is a Jordan homomorphism of associative algebras, that is to say, A and B are associative algebras. Sigma is a linear map, a map of, let's say these are, let's say F algebras, right? So these are algebras over some field F. And it's an F linear map that has the property that it preserves these two operations, this unary operation A goes to A squared, and this binary operation AB goes to ABA. So a map that has the property that it preserves these two things is what's called a Jordan homomorphism. It's a homomorphism of the algebras, but thought of as special Jordan algebras instead of as associative algebras. So if you have such a thing, and if B has no zero divisors, then sigma is either an associative algebra homomorphism or an associative algebra anti-homomorphism. All right, so that's what we're going to try to show. And last time we did a fair amount of this. What we showed last time, so that's the conclusion of the statement of the theorem. Last time we showed that for all pairs of elements in the algebra, that either we have, if you do sigma on AB, you either get A sigma B sigma, or you get B sigma A sigma. This seems very close to what we're looking for. The problem is the quantifiers are a little bit off. What we actually want, so this is what we did last time, but what we actually want is that we want, for every pair of elements, AB sigma is equal to A sigma B sigma. In other words, this is the statement that it's a homomorphism. Or, for all things, AB sigma is B sigma A sigma. That's the statement that it's an anti-homomorphism. We want either for all things this or for all things that, not for all things one or the other. Right? Okay, so it's a difference of quantifiers. Now, what we're going to do is we're going to argue that this statement is true by way of contradiction. So let's set up exactly what we're looking at here. So let's say from last time, we know that if I look at AB sigma, then this is equal to either A sigma B sigma or B sigma A sigma. And if we want this to be true, well, we're going to argue by contradiction. So suppose that there exists some A, B, C, and D such that, well, I want to say, suppose that A and B don't satisfy that. So in other words, so I want to say that suppose I have some A and B that don't make this work. So this isn't always true. And I have some C and D that don't make that work. That would contradict it being either a homomorphism or an anti-homomorphism. homomorphism. So suppose I have these things such that AB to the sigma is not equal to B sigma A sigma. And if I look at CD to the sigma, then that's not equal to C sigma D sigma. Suppose I have elements that fail both of these things. Well, what I do know also, though, is that these things, this holds. I mean, either this or that. So if AB to the sigma is not equal to B sigma A sigma, then it necessarily has to be A sigma B sigma. And if CD sigma is not equal to C sigma D sigma, then it necessarily has to be D sigma C sigma. Okay? So we're going to assume we have four elements that satisfy this, and we're going to prove that there's a contradiction. Now, such a contradiction would necessitate that this statement has to be therefore true, and then we would have either a homomorphism or an anti-homomorphism. Okay, so that's where we are. So to recap then, we know that this is true, and we're going to show that this thing has to give us a contradiction. Incidentally, if you think about it, what we're really showing is that if you are an element by element homomorphism or anti-homomorphism, then you have to universally be a homomorphism or anti-homomorphism. That's, I mean, because this is all we're really going to use here. I think. Well, we'll see if that's all we use. No, maybe we'll use some Jordan stuff too. Well, okay. Let's see what happens. So suppose that x in A is some arbitrary element. What I'm going to do is consider my four elements. So this is like a general fact for all A and B. These are A and B are kind of general elements of my algebra. We know this is true, and this is my assumption, is that I have these four special elements. Okay, so I'm going to fix these A, B, C, and D forevermore. Now let x be an A, and let's consider A plus xb. Well, we know that. Well, actually, that'll confuse me if I do that. How did I have it in my notes? Let's look at A, B plus x. And do sigma to that. So, what do we know? We know this is either equal to A sigma B plus x sigma, or it's equal to B plus x sigma A sigma. So that is to say it's either A sigma B sigma A sigma x sigma plus, or it's equal to B sigma A sigma plus X sigma A sigma. And also we know that this is also equal to AB plus AX sigma, and sigma is a linear map, so we know that this is AB sigma plus AX sigma. Okay? Now, so let's think about it. Is it possible that right, so what if, so suppose the second thing holds. In other words, suppose we actually have that AB to the sigma plus AX to the sigma were equal to this thing. What would that tell us? Well, if that was true, and if AX to the sigma was equal to X to the sigma A to the sigma, then we would actually be forced to conclude that AB to the sigma was equal to B sigma A sigma, which we know is not true by our assumption about A and B. So therefore, if this is equal to that, then we have to have that these things are not equal. And if these are not equal, then that would force us to conclude that, because you know that either AX to the sigma is this, or it's equal to A sigma X sigma. Okay? So if this expression is equal to the second guy, then we're forced to conclude that AX sigma is A sigma X sigma. On the other hand, if this second conclusion doesn't hold, if we don't have this, then we must have that. So otherwise, so else we're forced to have that this thing is actually equal to that guy up there, a sigma b sigma plus a sigma x sigma. But if that's true, we also know that these guys are also equal, and so that would imply that ax sigma is equal to a sigma x sigma. Which is to say, no matter what you do, you always have, for any x in A, you always actually are going to have that a x sigma is equal to a sigma x sigma. Okay? So there's a number of variations that you can play on this game. I could have put the x next to the a. I could have looked at a plus x times b. I could have done the same with the c's and the d's, and you can do a similar argument for each of these cases. And I won't do them all because the pattern becomes clear very quickly. So let me tell you what you find. So for an arbitrary element in A, we can actually show that ax to the sigma is a sigma x sigma, that xb sigma is x sigma b sigma, and in terms of the c's and the d's, if I were to look at cx to the sigma, then that turns out to be c sigma x sigma. And if you look at xd to the sigma, then that's equal to, oh, I'm sorry, this is backwards. The c's, you get the reverse there. And for xd, you get d sigma x sigma. Okay? So for all x in A, this, I just recopied that line over here, so let me erase it. Let x in A, then you can show that these four things must hold. Okay? Okay. So then, to finish this off, what am I going to do? Let's look at a plus c, b plus d. Okay. So, yeah, I guess, you know, see what's going on here, right? I mean, like, the A and the B have the correct homomorphism property, and the statement is that if you replace, you know, B with an X, then it'll still get the right homomorphism property. The A will force it to have the right homomorphism, the correct homomorphism property, and, you know, if you replace the A with an X, the B will force it to have the correct homomorphism property, and the C and D will make things inherit the anti-homomorphism property. Okay, now let's look at this. A plus C, B, D, what we know is that either you'll have the homomorphism or anti-homomorphism thing holding, so you'll either have, sorry, if I do sigma to that, we'll either have A plus C to the sigma, B plus D sigma, or we'll have B plus D sigma, A plus C sigma. But we also know that if I could just FOIL this out on the inside first, and get AB plus AD plus CB plus CD to the sigma, or in other words, I have AB sigma plus AD sigma plus CB sigma plus CD sigma. Okay. Now, what I want to show is that this is equal to neither of these two things, and that would give us our contradiction. So, for example, if I have that this thing was equal to this first guy. So what is this first guy? Of course, I can do the sigma and FOIL it all out, and what will I get? I'll get A sigma B sigma plus A sigma D sigma plus C sigma B sigma plus C sigma D sigma. And these two things are actually equal because of the property of A and B. These two things are equal using x equals d. These two things are equal. So these are equal using x equals d. These are equal. These two things are equal using the x equals c. And so if this is equal to that, then I can subtract, 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 and I'll be forced to conclude that these things have to be equal, but guess what? They're not. Contradiction. So this cannot be equal to this first thing. But similarly, it can't be equal to the second thing, right? Let's see what would happen if we tried to make it equal to the second thing. If it's equal to this second thing, FOILing that out would give me a B sigma A sigma, B sigma A sigma, plus B sigma C sigma, plus D sigma A sigma, plus D sigma C sigma. Okay? Now, by hypothesis, we know that these two things are actually equal. That's what I know about the C's and the D's. Now, these guys are actually equal using the using x equals d and using this equality right there. X equals a. I'm sorry, x equals a. And these guys are equal using the identity with the c of x, using b equals x. So these are equal, these are equal, these are equal. Subtracting things off makes us conclude that these things are equal, but they're not. So that gives another contradiction. So this cannot be equal to that nor that, and therefore we obtain our contradiction, and that concludes our proof. We are either a homomorphism or an anti-homomorphism. I guess it's interesting to note, yes, we didn't actually use anything about the Jordan structure for this part of the argument. So in fact, it's kind of self-contained. The statement then is that if we have an associative algebra, or a pair of associative algebras A and B, and a linear map sigma between them, so maybe I'll just record this for the sake of posterity or whatever, that we've actually shown that if sigma from A to B is a linear map, such that for all A and B, this is equal to that, then sigma is either a homomorphism or an anti-homomorphism. So if it's an element-by-element homomorphism or anti-homomorphism, then it is actually a homomorphism or an anti-homomorphism. Thanks.